So we last session we talked about some layout design rules, right? And we discussed okay, in case we have a kind of a particular process that says it has two poly layers and four metal layers, okay, and we know that a lot of processes have this kind of configuration. So it means we understand that there are two poly, so poly 1 and poly 2 would be two such layers, and I'll have four metal layers, right? So it means I have metal 1, 2, metal 4. And why do we have such processes? It depends on the technology. That There is a technology called CMOS process. There is a technology called as SOI process. SOI stands for silicon over insulator or silicon on insulator. So there is also one process by CMOS. So it means in this particular process, you not only have CMOS transistor, but you also have BJTs, bipolar junction transistors. And there is also so many other processes, but most common process is CMOS. And sometimes you have by CMOS and all that. So when I talk about, we last session, we talk about, okay, when we talk about the metal layers, metal 1 and metal 2, or diffusion layers or polysilicon layers, and we also talk about the contacts right over here, and we also talk about the vias, okay. So we talk about that when I draw a rectangular like this for any particular layer, I need to satisfy the minimum dimension that is defined by the technology. I cannot exceed that as a designer, as a physical, as a layout engineer. I cannot do that. So what does that mean? It means I have a special design parameters. Just for my understanding, I call it as lambda. It's a layout design rule parameter that tells me its value is half the minimum feature size given in the technology. Okay, so based on that, I will just say if I am using a 10 nanometer node, I know that lambda would be accordingly defined. So when I talk about metal 1 here, you see, I see that the minimum length, the minimum width actually is 4 lambda. Okay, so it depends on what is the feature size, I will accordingly have this dimension. Then I want to, my circuit is in such a way that I have two metal adjacent to each other, so the minimum spacing between them I see has to be satisfied, which is again 4 lambda. So metal layer 1 I have shown by these lines. I have used the same color but different way of showing the metal 2 layer. So again the rules are same here. Okay, what about I have more layers? Like I said, I have metal 1 to metal 4 layers. So I need to, as a layout engineer, what I need to understand is that if the technology is having more layers, so higher the layer I go. So I start with this metal 1, I call it M1. Then I have this metal 2 right here. Then I will have this metal 3 and so on, right? So what I see is that the higher I go from M1 to M3, this is the top view, this is the cross section actually we are looking at. So I will have the higher thickness, that is the thickness of these layers will be higher as compared to the earlier layers. Okay, so M3 will have a higher thickness and the larger width, it would be wider also. Okay, M3 will have higher thickness and the width than M2. M2 will have higher thickness and the width than M1. Why? Because that provides me a lower resistance, lower electrical resistance. So this is a metal. If I have a lower resistance of the metal, it means it will act as a good conductor, and ultimately I am using the metal layers for the routing purposes, right? To connect the things, to connect the circuit from one point to another point, I am using the metal layers. It's just like you are using the soldering some circuit on the printed circuit board. So you are using the metal wires and you connect one node, you solder one node from one point to another point. So it's same principle. So lower resistance, because of that, because it is thicker and wider, I will have a lower resistance. So we also see that diffusion. Here I see that the minimum dimension is 4 lambda.
Sir, going forward, we are using an thicker metal now, sir. Why we are going forward we are using, not in the initial stage.
I didn't understand your question again.
Let's say we have M2, M1, M2, M3, three layers, right? So M2 is thicker than M1, M3 is thicker than M2. So the reason is M3 is having a low resistance. Why are we not using M1 itself as a lower, resistance? Going, higher layers, we are using thicker to reduce the resistance. What is the requirement to reduce the resistance when we are going more than one layer?
Okay, no. Once again, understand what I said. I am saying if you have like 3-layer process, I have 3 layers available here. The thickness of one M1 is already there by the set by the technology, set by the foundry. It is say 1 micrometer, and then M2 has a thickness of 2 micrometer. M3 has a thickness of, let's say, 3 micrometer, and moreover they can be drawn wider also. So it has a certain width limitation that I will use, but it can be drawn little wider, it can be drawn even wider. So that technology library allowing me to draw these 2 layers wider. They are already thicker, that is already defined, and I am allowed to draw them wider than the earlier versions, because that will offer the the resistance of the wire rho L over A. So if I have a larger, A is width into thickness. So if I have larger width and larger thickness, the resistance is coming down. You know that.
No, sir. Yeah. See, M2 is having a lower resistance compared to M1. Why are we using like that? What is the requirement to
We are not
reduce
using
the?
that. That is already foundry defined, and for
Okay.
that we just are having. I said the lower resistance will give us. They will act as a good conductor.
Okay.
Conductor has ideally no resistance, right? So
Yes.
lower resistance means they will be a good conductor. Ultimately we are using them for routing, and they are acting as a good conductor.
Okay, sir.
So here you have 4 lambda for diffusion. Again, if I have 2 diffusion areas adjacent to each other, so I have to satisfy this rule. Same for the poly. I see the minimum spacing between the 2 poly. If they come, the circuit is designed in such a way that these 2 poly lines are coming next to each other, adjacent to each other. So I have 3 lambda. And then the minimum width is 2 lambda. That is how. Same we saw that, okay, now I have metal diffusion contact. Where I need this contact indicated by this black square, I need here, because when I draw the diffusion, this is source and drain of the particular NMOS transistor, and then I'm drawing the routing here through the metal wire. So obviously metal will connect to the diffusion only when I will etch this area, or I will make the cuts here. So that's why we need the contact. So their rules also set the minimum contact, this could be 2 lambda by 2 lambda, and the region around it would be spacing, all directions would be minimum 1 lambda. If I have to make a connection between metal one and polysilicon, like I said that you once you draw the gate here with the poly, you can have the metal just for the external routing, right? Poly is just to form the gate, and after that you can use the metal here. So that metal and polysilicon, the contact will come here, for instance. So that says also that has a predefined rule. What if I want to connect metal 1 here, that is making this one, and then I have on top of that I have metal 2. So I want to connect these 2 layers. Why I should have, why also there is a question why I have so many metal layers, because it allows me to make number of interconnections, right? You have so many options, so you don't overlap each other, rather it's just like a multi-story building, first floor, second floor, third floor, and so on. So you have different metal layers you can use without, instead of using only single M1 layer. So if you have only one layer, your circuit will be congested and there may be a lot of overlap. But you have a large number of layers, M2, M3, M4, you can use those layers. So if, for example, this shows metal 1 and metal 2 are connected with the special contacts, they are called via, and they look like this. So here is how I am making the connection. This is a cross section, and if I look from the top, they looks like this. So you see now there are two metal layers. This is one shown by these arrows, and in the same diagram I have these dots. So this is this layer. So M1 and M2 are placed on top of each other and they are connected by this via, the square box. And similarly, there is a distance between two vias should be 3 lambda. So all these rules are to be satisfied, and the tools, automated tools, come there to help you to stick to these rules. When you violate, like I explained earlier also, these rules will tell you that which rule you are violating, and accordingly you will be getting the DRC error. Then your job is to go back to your software and see again where I am violating the rule, because the tool itself will take you to the position to show the error. Just like you are in a software, few of you get some errors, so you are now dealing with the hardware. So those errors are about your software and these errors are about your hardware. Okay, so having said that, now we want to understand another concept that is called as transistor dimensions. So what we do here, you have this transistor like I said before. So you have a drain, you have source, and then let's say you have accordingly you make the connection. So it has a width and it has a length. What is length? Length is the channel length. This is the distance between source and drain. And width is, if you see the cross section, like many of you have drawn here, I earlier said, so it looks like this. So you have like this is P substrate, and then this was N plus region, this was again N plus region, and then you have a small oxide here, and then you have a gate here. Okay, and if we look the three-dimensional view, it looks like that, right? So you can see now, so if the channel length would be this one, this would be your channel length L, the distance between source and the drain, and the width would be how wider your transistor is, because if you have the polysilicon gate length, this is the rectangle that you are using. For example, this is the rectangular if you use here, so this is the width of your transistor. Okay, so the wider the width, the bigger the transistor dimensions. So transition dimensions are often specified by the W by L ratio. So you will also need to remember this, what is W by L ratio. L is the length, W is the width. So if I have a technology with a channel length or feature size of 10 nanometer, I am using this one. So I draw this transistor. So obviously the L here is, I see that the L here, right here, is 10 nanometer. And if I have a W equals to 40 nanometer or 50 nanometer, let's say 50 nanometer. So what is gonna be the W by L ratio?
5.
Right. So what I do here is that I will, when I draw the circuit, for example, I will draw a circuit like this. I have this circuit. So let's say you have input here, you have output here, and VDD and ground. So I will just, when I will indicate, let's say this is a 10 and this is 5, and I'm drawing this circuit using 10 nanometer feature size. So it means I have a 10 W by L ratio of PMOS transistor is 10, W by L ratio of NMOS transistor is 5, and technology is 10 nanometer. What is the width of each of these transistors? The width of the NMOS and width of the PMOS.
50 and 25.
No, L is 10 nanometer. So obviously width of NMOS would be 5 times 10, 50 nanometer. And the W for the PMOS, it would be 100 nanometer, right?
Yes, sir.
Right. So similarly, this is how you can always define your transistor ratio. So sometimes you will see on the schematic, sometimes you will see that the circuit is drawn, and they will say that this has a ratio of 10 by 2, and this has a ratio of 10 by let's say 10 by 1, something like that, or let's say this is 10 by 4 and 10 by 2. So how to understand this?
10 nanometer width, channel length is 4
Channel length,
nanometer.
the feature size is 10 nanometer. The feature size is 10 nanometer. I can define this ratio also. This is the ratio is 5, and this is the, like, say 2.5. 2.5.
So W divided by L is equal to feature ratio.
No, W by L is the transistor dimension.
So is there any term for that?
No, we just say W by L ratio.
Sorry?
We just say W by L ratio. W over L ratio.
Okay, sir. Future size means channel length.
Yeah, feature size is the technology, physical dimension of that transistor. The minimum dimension.
Okay.
Okay.
So what is called as a channel length term?
They are all the same things. Feature size or technology node, they say 10 nanometer. This is what they say, or we often hear, or we often see these kind of words. Then physical interpretation, physical meaning of that is, it's nothing but the transistor size. And I just explained you, this is the distance between source and drain. And what is the distance between source and drains? We call it as a channel. So they are all same thing, but you will hear these two words more often than the channel length. Channel length is used for the analog domain more often, but for the digital logic you can just understand these two. Keep in mind these two words, feature size or tech node. They say 10 nano, 20 nano. It means you just say this is the minimum, smallest transistor available in that technology. Understood?
Yes, sir.
Yeah. So now there is another look at this layout. What is this layout looks like?
Inverter.
What is this circuit? Inverter, right? So you have this diffusion here, you see, this is the source and the drain of the transistors, and then I have a metal here where I have routed, and I'll connect to ground. Then I have this transistor, and the width of this transistor is this one. This is the width of the transistor, and this width seems to be double than the width of the NMOS. So this is PMOS. See, it is sitting in the N well. So, and the poly is drawn the gate of the transistor over the two gates of the transistors, right? So here is your drain of the this is source, and this is VDD. So why this PMOS is shown as in dimension is shown twice to that of NMOS is because NMOS has electron as the charge carriers and PMOS has holes as the charge carriers, and the mobility of electrons is greater than mobility of holes, right? So if the NMOS has a current flowing through it 1 nanometer due to electrons, then if you use the same dimension for the PMOS as you use for the NMOS, it will have, for the same dimension, the PMOS will have the current magnitude of about only 5 nanometer, but you want same transistor for PMOS to conduct as a switch. So to make the same magnitude of the current flowing through both the transistor, you will make the PMOS dimension twice to that of NMOS. So it will have 1 nanometer current magnitude in NMOS and PMOS. So that's the reason. So in digital design, if you have a technology size of 10 nanometer, will you choose the L to be 50 nanometer or greater than 10 nanometer? No. Why? Because for the switching, I know that the lowest channel length or lowest physical dimension of the transistor means my transistors are faster, smaller, and they will consume less energy. Okay? So this is an example that we have seen now again. So use this word in IC design. You will also always hear this word called as cell. So you will hear this word about cell, module, functional block, and all those things. These words you will hear. So cell means it's just a particular instance. There is another word you call it as an instance of some logic function. So for instance, this is a cell of an inverter. It means I can also call it as it's a cell of an inverter using a set of inverters, or maybe set of, we have seen the inverter buffer also. I can create a module of latch, right, or multiplexer for instance. Then using a set of multiplexers, I will create a module of a latch. We have used mux to create a latch. Then using a latch, I will create I will create a module of a flip-flops, right? So we have seen that. So let's see how this inverter layout looks like. Now you need to understand these layers very well, because I am repeating this. Once you have a good exposure and good understanding of what each layer is, how they are drawn and how they are connected, and dimensions of these from each other, I have already told you. It will be easier when you will draw the layout for the larger blocks, because most of the time you will be designing a small module. So like I said, module means you will have different cells: cell for inverter, cell for mux, cell for latch, cell for flip-flops, cell for registers. Using these cells, you will try to create some bigger function. For instance, you want to create a memory, right? So like I said, the set of register, you will put all these registers like latches, then you are creating one module of a register, n-bit register. So of course, if you know the individual layout of one cell, it would be easy for you to understand the layout for too many cells which are interconnected to each other, right? Their understanding. So for that, you need to have a good understanding of this one. So let's take a look again. This gray layer is, which area is this? N diffusion. This blue area right here, P diffusion. Do you remember the layers we have seen this?
Yes, sir.
Then this line, solid lines indicate metal. It could be metal 1, 2, depends on in that process, but for simplicity we'll still say it's metal. And then we know that this black rectangle with these lines inside like this, that's my poly. And this black one, please unmute yourselves, this poly, and then I have these blacks, they are what? Contacts, right? So now how we are connecting? So this is my source. Let me track the another this one. So this is my source, this is my drain. I draw it here, source and drain, and that's my NMOS transistor basically. So simply what I do is that I am drawing this diffusion area, and I know that here is my source, here is my drain, and how they will be separated when I will draw the polyline on top of each other. As soon as I draw the polyline, by the technology the width of the poly is already set. So once I draw the polyline, I know that this is nothing but the channel length. This would be channel length. So the width of the poly itself will set the channel length during the fabrication of this transistor. Okay, so what I do here, see the poly is drawn here, which is overlapping little bit over the diffusion region, and then I go up. I here draw the diffusion region in blue. This is the blue in the center for the P diffusion. So that's my PMOS transistor. So again I am drawing it somewhere. So I extend this one, and somewhere here I am saying that I want my PMOS transistor. So let's say this is the diffusion region, and I am extending this poly so that the source and drains will automatically be formed. So this is a poly, and this is the source and the drain of the PMOS. And obviously what I need to do is that poly is drawn, P diffusion is drawn, this is NMOS, this is PMOS. Once you get a good understanding of this layout, you will be easily able to interpret and understand a very big layouts where let's say there are hundreds of transistors are connected. So you can differentiate the routing and all those things. So poly is done, N diffusion is done, P diffusion is done. Where is PMOS will be fabricated? This gray area. This is N well. This gray area. So I know that this transistor is sitting in the well. So I will just draw some other color I will use just to differentiate. So let's say I am drawing the N well here somewhere. Okay, so that's my N well right here. So you see in this gray. So that's all. Now what I want the metal layers. So metal, I am forming the circuit of CMOS inverter. So I know that here I need contacts. So I will first draw the metal, and that's my VDD. Then I know that source and drain of the NMOS and PMOS are connected. That forms the output Y. The gates are already, I can draw the metal here also, but just simply I will say it's the input A. Okay, but with the metal also, no problem, I can draw the metal. And then I see now this is covered, the source, and then I have this ground here. Just I'm repeating this layout. So routing, what I just did is, the process is called routing. Just keep taking the notes so that you use these words often. You will hear these words, and this will be helpful for you to understand. So this is how I will do the routing to interconnect the transistor together. But it was, as I said, this is a very simple cell of an inverter. What about did I miss anything with this inverter circuit? No, or yes. What about the body of the transistors? I have a body of N well, but I need to have access. I want to reach out to that, right? I cannot keep it floating. Why? Because I said if these two transistors, the bodies are kept floating, so they are high impedance nodes. I can say any voltage can come here that can interfere with the operation of this. So what I do is that the body of NMOS is tied to its source, and they are ultimately both are tied to VDD. The body of PMOS and body of NMOS is tied to its source, and these two ultimately are connected to ground. So what I am doing is that, look at this figure, same inverter layout, just little adjustment. Here I am doing one more contact here, and that is giving me access to the substrate tab. But where is the substrate here? How I am seeing the substrate? How will I have access to the substrate? So you see here, this blue is the diffusion area first, isn't it? Look at the difference between two layout. I am just wanting, in the second layout, I just want to make the body connection for both of these transistors. So what I am doing is that here we are looking at the top view, right? So here the blue shaded region is P diffusion area. I just did the fabrication procedure just like in the previous session. I performed those steps and I got this dopant here, and then when I put this metal here, so through these contacts 1 and 2, I got this contact here etching, so metal got connected to this p diffusion area. So I would say that I got connected to the p substrate. Here is my p substrate also. This is n plus, this is n plus, and this is p plus, if you remember. So I got metal now connected to the p substrate. For the n well, here is my n well. So I know that I need to add dopant and call it as a n well. So what I do is that this gray shaded region in the well itself I am having, that is called n diffusion. So once I formed the n diffusion, I added the dopants, then I routed this metal line like this metal line. So it got connected to this diffusion of the PMOS also and the diffusion area of the NMOS also through this contact etching. Okay, so I say that now my metal is also connected to N well, and the metal is also connected to the P substrate. So you see, when you will use the transistors from the library to draw the layout of a particular circuit, so you will already have these ready-made cells. What does that mean? You will have a transistor with this, and somewhere the body will also be connected to its N well. You will have this cell already with diffusions and the contacts established. You only need to draw the routing of poly and the metals. That would be the case when you draw the layout for the larger cell, a complex circuits. Now an exercise for you. This shows a layout for the 3-input NAND gate. So what I did is that I had the transistors in the library. I picked up them in a particular process, and then I just made the routing. I use the word again, routing in the sense the transistors were ready for me with, like, let's say this was the cells I directly got. When I take the when I take the transistors from the library, something it looks like this. You will see in this in your library. I always will have this kind of transistor. So I will say this is the ready-made cell for the NMOS, and similarly I will have the cell for the PMOS. So I will just take these transistors and then I will connect them together. Okay. Now, can anybody tell me how I arrived at this layout?
About three are PMOS, they are in parallel connection.
Yeah, but my question is that, let's say you are working in a company and I give you a job of, okay, I'm a manager, and I said my team, okay, one of you, I give a task of, let's finish we got the job, we got the project, and project is we want to complete a layout of 3-input NAND gate. So you somehow you draw this, but how will you start the process?
First, I will write that 3-input NAND gate symbol. After that, I will write an CMOS structure, NMOS CMOS structure. So NMOS CMOS structure will be above 3 PMOS will be in parallel. After that, below 3 NMOS are below 3 NMOS are in series. So this structure I will write. So and then I will do the input output connection. The above one is the VDD, below one is ground. According to that, I will write this layout design.
Okay, that's correct answer. So what I know is that so I am now calling it again the cell. So I am given a task to draw a layout for a cell. What is that cell? It is just some logic, and logic is y equals a and b and c, and it's a NAND function. So I know that the schematic of this NAND looks like something like this. This is, let's say, A, B and C, and I know that I have to use these parallel transistors of the PMOS right over here, right over here, and then I have this VDD, for instance. So these are, let's say, A, B and C, and there are three inputs, and somewhere here I have a Y. So what I can first understand is that let's say these are the drain, source, drain, source, drain, source, and that's source, drain, source, drain, and source and the drains of this transistor. So I know that my schematic looks like that, the circuit diagram looks like that, and I know what is the logic I want to make the layout for, and accordingly I start the process. So what I'm doing here, just try to have a look at this. I first start with the NMOS, that is the pull down logic. This is the pull down network. So can you see the active region for the NMOS? This is my NMOS transistor, right? But I have 3 in series. So what I'm doing is that 3 in series means instead of taking 3 individual transistors like this, 1 and then again 2 and again 3, I can draw one single transistors, right? So total L of this transistor will be 3 times L, right? Let's say TL, that is the total length of this transistor. So that's how the series connection is made. So you see now how I see this, they are the 3 because in between there is a polysilicon. So look, see, this is the first polyline, this is the second polyline, this is the third polyline. They are crossing over this diffusion region. The gray shaded region are nothing but the diffusion. So where are the drain and the sources of these transistors? So I will just say, okay, this is the source and the drain, this is again the source and the drain, this is again the source and the drain, okay, and I just make the contacts at the end of this. So you see the drain and the source of this here, there is a connection, so this area, so they are just series, so right, this area also is common. So that is how these poly layers are separating the 3 transistors. They are actually, you can also understand that that is one single transistor with total length equal to 3 times the individual length. So that's how I got this layer. So when you want to actually make such transistor, the tool will help you. You can simply say you have to define W and L for each transistor you will take from the library. So once you select particular transistor from the library and you will double click this instance, I am now calling it as instance, the parameter window will open up and the parameter window will allow you to set W and L. So if I set L equals to, for the 10 nanometer physical size, I set L equals to 30 nanometer and W is for whatever W, so transistor will look longer. Okay, this is the transistor that I will have in the window to be placed. So just to tell you details, because these details are very important for you to know and it will help you. So once I am done that, what about the PMOS now? How many transistors I see here? Again 3 transistors. How they are connected? They are connected in parallel. Okay, so what I do here, can anybody tell me how we are making the routing here? Routing will see just very simple. This is our NMOS is done. Okay. Oh, I just deleted this. We shouldn't have deleted that. Okay. Let me draw it again.
Control Z. Control Z. May work.
Okay. Let's see. No, it's not working. Okay, no problem. So we just see that. We just draw it one more time, no problem. So we know that how we are making the connections. So that's VGD, that is source, and these are the drains. and these are the gates A, B, C. Okay, and this is output what we have, and then we have this A, B and C. So we know that A and A, that's a common input, B and B, that's again a common input, C and C here, that's a common input, that's your ground here. Okay, and now this is your drain and source, drain and source, drain and source. Okay, so now for the PMOS, so I know that drains of these three transistors at the upper level, they are shorted to each other, right, and the sources are connected to VDD. So what I see here, I just try to understand what is my schematic. So here is my source, drain, and then again I have to, this is drain, source, no, 1 second,
drain, sir.
okay, wait, just yeah, this is my single transistor. Okay, so this is source and the drain. Okay, let me write here source and the drain. This is my second transistor, so this is again drain and the source, and this is my, now we made a mistake again, wait, don't get confused here. Simple way to understand the transistors are, let's say they are separated. This is gate 1, gate 2 and gate 3. So either side of this polysilicon are my sources and drain, right? So let's say we'll call it as, let's say, source and the drain, no, once again there is a problem here.
No, sir, after poly drain will come.
Yeah, after poly drain will come, that's correct. So poly here for the first poly, so this is source, and then let's say this is the drain, then this is drain, this is source, and yeah, and this is again drain and this is source. Okay, so this is individual transistor, the drains are overlapped. This is second transistor, I use the different color, and this is the third transistor.
So the last one, the third transistor, drain and source should be with us.
It's okay, that can be interchanged because we know that it's a symmetric structure, right?
Yeah, but
you can write that convention. So I'm just trying to forget about which is, say, a source and which is drain. Just say that the drains are overlapped, right? Over here.
Yes,
Yeah. So now the one end of this transistor is connected to the source, to the VDD. Where is the connection to the VDD? Look, here is the connection to the VDD, and here is the connection to the VDD. So did I say, can I see that all my three transistors in the pull-up network, which is nothing but the PMOS, their sources are connected to the to the VDD?
yes, sir.
Yeah, this could be source and this could be drain, right? Yeah, so now that is done. So I am done with NMOS, I am done with the PMOS. What about this connection? The drains of all PMOS and the drain of this upper NMOS, they are making a common point, and that is fed to the output Y. So very simple. Where is that common point? Look here, drain of this transistor, then drain, these two drains are shorted together again, that is, so this is my common point, and this is also going, this blue metal is making contact with the bottom NMOS, and this is nothing but my output Y.
Sir, while connecting, there it's supposed to be a metal contact, no, sir.
Yeah, so I'm using the metal lines only.
A metal contact, but block.
Yeah, metal contact. So see, here is the one contact, and here is another contact.
While joining both them, it is pull up and pull down, we don't have drain and drain are
Right. So first see, these drains contacts are made here. There is another contact here, right? So I got contacts with the drains of all the PMOS, and now I want the contact of metal with the drain of a NMOS. So here is that contact. You see, the total metal length is like this, metal line is like this. Can you see now? Yeah.
The stick diagram and layout both are same, sir?
Pardon?
Stick diagram and layout both are same, sir?
I couldn't hear you properly. Come near to the mic maybe.
The stick diagram and layout both are same, sir?
Yeah. So we are drawing the layout of this circuit only. Right. So see, once we have done and the poly layers are done, now you might want to understand that there is a overlapping. It looks like there is a overlap between poly and the metal here. You see, these metals and the poly is drawn like this. So are they shorted?
No, sir.
No, because they are on top of each other. This is the top view we are looking at, right? So, and this is how you will draw the layout of the signal. So this is just a simple layout of a 3-input NAND gate layout. So NMOSes are connected in series, PMOS are connected in parallel. Once you take these cells, you just draw the poly to separate source and drain of each transistors and just make the metal routing. Just define the VDD and the ground and make the metal routing right. Now how about the size of the chip? Let's say this was your assignment to design a chip physical layout for this 3-input NAND gate. How do you come to the what was my size of the total NAND gate that I drew? How will you estimate that roughly? For instance, you just know the information about technology library 10 nanometer and you now know the lambda rule, right? Lambda rule is L by 2. So you know the layout technology rules. You know that what should be the minimum width for poly, what should be the minimum width for metal, what should be the minimum width of diffusions, and you also know the rules between the spacing between them. You also know the rules, all these rules you know already. So when you will follow these rules and accordingly just by hand, pen and paper, you can just roughly estimate what is the approximate size of this particular cell when I will finish the layout. So that shows here, for instance, total size is 40 lambda by 32 lambda. So let's say LO technology is feature size. Feature size is 10 nanometer. So can you tell me the size of this chip? It would be 32 by 5 nanometer. How much? 150. And this would be 40 by 5, 200 nanometer. Yes or no?
160, sir. Nanometer.
Yeah. Okay. So this is how you come to roughly estimate that one. For the larger designs, how will you estimate that size? If suppose you want to build a layout for the master slave flip-flop. So master slave flip-flop, you know that you have transmission gates, master and slave. You have clock also. So there is another circuit which will generate the clock, right? And you know that how it works. So you know the logic table, you know the logic equation, you know the clock timing diagrams also. You have a clock, then you have an input, then you have an output when the master works, when the slave works, everything you know now. So now the next step would be to design a physical layout for that particular cell. Yes? Any question so far? No. So when to have a rough estimate about, to draw roughly the layout of any cell, and also to have a, based on the design rules, to have an approximate area that will be required for my chip. The layout designers, layout engineers will always often use the concept called as stick diagram. This is there in your syllabus also, stick diagram. So stick diagram is basically, I just simplify my layout. For instance, you see I have to draw this extra space and well maintained, and I have to show properly all these areas and all that. So stick diagrams helps me with the number of layers I have to quickly draw the diagram for each of the cells. So for instance, this is the stick diagram for an inverter. So what I did is that I quickly have the N plus active area and diffusion area. I have the P diffusion area. Then I know that there will be a contacts here, because to have a contact between sources and the drain, this is the sources and the drain. And then poly will be drawn exactly from the center to separate the sources and the drains of each of these transistors. So this became input, that became output, and I just draw the metal wires using these layers. So stick diagram is for that. Similarly, this is the stick diagram for 3 input NAND gate. So very simple again, I have a long NMOS transistors, 3 gates. It means I have divided the single transistor into 3 equal length transistors. Similarly, I have a transistors which is PMOS, and because that's the NAND function, 3 input NAND function, the layout and the routing will look like this. So very simple. So you can have any logic function. So assignment for you is to give me a stick diagram for 3 input NOR, 2 input, or let's say 3 input NAND is done, NOR is done. Let's say give me it for AND also, AND gate and OR gate. So these 3 input. Okay, so this is your assignment. So just little more terms here. Pitch of a routing tracks. So these are routing tracks all the way, what we see here. So when you draw the stick diagram, that also helps you to quickly understand how the layout will look like for a particular cell. So you see now, for instance, I know how to have a layout of an inverter and a NAND gate. So definitely if I make the interconnection between these two with some idea, what logic function I am coming at?
AND gate.
Right? Is this the only way and the proper way to create the AND logic through circuit diagram or layout, or like we had discussed this point, or there is another way by which I can design and fabricate AND gate, or is this the only way that seems?
No, sir. As you said, there are different ways.
There are different ways. So there are 2 levels, 1 level, 2 level. Why can't we simply, there was our discussion about why can't we just without inverter use it, right?
Yes, sir.
And what was that discussion?
So again, I gone through some of the information. So there, I didn't get anywhere that without inverter they are, constructing a NAND gate. But as per earlier discussion, using an, inverter, ulta, if you do that, that is acting as a buffer. And you said that that buffer is an, you cannot use, because of it will not provide a strong zero and strong one. Maybe by using that method, we may construct AND gate without inverter.
Good. Yeah. So we want to have a restoring logic. Restoring logic is, in the sense, we want to have a strong 0 and 1 switching between the two, logic 0 and logic 1. We don't want degraded output. That's how we will use this. So simply, if I ask you now to make these 2 stick diagrams, to connect them in a way that will create AND logic, will you do that? Yes, right? It looks simple. So you know how many metal layers, how many layers are there. Accordingly, you can just create a layout, physical layout for any cell. And these are some rules again. So what I see here, yes, any question? No. So 4 lambda, it seems the metal width, there is a spacing between that I must follow. If I violate, I will run the DRC. What is the difference between these two? Okay, this is just the width of individual metal, and there is the spacing. That's the one rule. That is called as pitch concept, because these layers and these rectangles I am going to use as a routing tracks, just like I have used this. These are all routing tracks, the way I am connecting them, way I am placing them. Okay, and as a designer's habit and choice should be to make the layout as compact as possible, because if you have only limited area, 100 micron by let's say 90 micron, so you got to have only this area, and you have to fit your design within this one. You cannot violate, because that will not solve the purpose of chip design. Whatever is assigned to you, you have to put your logic function inside that area also. Here is this metal layer 2. This is, we call it as a metal 2. This is metal 1. Alright, again there is a 4 lambda width, and the spacing between has to be a 4 lambda. So these design rules are specific for a are there for a specific technology node. For example, 10 nanometer. If I am using a 2 nanometer technology, or let's say a 20 nanometer technology, I will have a different width and spacing rules. So just try to understand this one. Okay, now look here. What is the difference between this and this square, which is all filled in, and this is not filled in? Because when you will look the layout as an engineer in the EDA tool of, there are hundreds of transistors that have been interconnected together to make, let's say, master slave flip-flop or decoder, 8:1 decoder, or a simple memory, whatever logic that can be. And you will see all these field dots, or let's say these squares. I just explained you what is this. So you need to understand metal contact with what, which layer. Metal is connecting to which layer?
This is metal.
This is one pair and this is second pair. Yeah,
One is connected to the polysilicon.
okay, tell me this layer or this layer, they are same. Metal 1 is connected to
polysilicon.
correct. You see this black, we have defined this layer earlier. This is our polysilicon, right? And on top of that, with the blue line, I have drawn this one, and there is a contact, says there is a connection between these two layers. What about this or this? They are same.
Metal to metal contact.
Metal to metal contact. So dotted metal is metal 2, and the lined metal, solid lines, they are metal 1, and I know that they are connected to each other, so I will show that. And this is called as contact, when metal connects to any other layer except metal. And when metal connects to metal, that is called as via. Okay, so we teach all these very fundamentals and very important terms to our students at our institutes. So try to take the notes of this, and it will be helpful for you to understand, to interpret the bigger layout when you will do that. So this is called via. In the cross section, how will it look like? I have M2, I have M1, and I will just draw this one, and I will say that it's just like two pipes or two bricks are connected together with the pipe, or there is a pillar here, something like that, just as a constructive term, something like that. Okay, what do we see about this diagram? Gray area is diffusion. Okay, what is this shaded? It means I have drawn the metal overlap with this diffusion, and there is a contact. It means there is already a contact metal is making with the diffusion area. This could be source or drain. Another here, again a metal, I am making contact with the source or drain, and the poly is saying again poly. Poly means this width of the poly sets the feature size of the transistors. You cannot draw the poly width to be larger than what is set by the foundry tools. So these some rules are followed. The next would be, if suppose I have to create the inverter circuit and I have a transistor cell for the PMOS. For instance, let me draw again. So for the inverter I have taken from the library for the PMOS, and just very near I am just placing the NMOS. So there is actually this polys are coming together, poly of NMOS and poly of PMOS. Will it work? No, there is also a rule for that. So it says that minimum 12 lambda should be followed for this particular technology. For another process there will be another rule. So it says, what is this area? N well, because I am having a separate body for the PMOS. So this is source or drain of PMOS, this is source or drain of PMOS, is here poly, and then I have this. And then it says from the active diffusion area of the PMOS to the active diffusion area of PMOS, I must leave the space of about 12 lambda. So it means if I'm using the technology of 10 nanometer, what should be this distance? Interview questions.
10 nanometer?
Yeah, I have a feature size of 10 nanometer. Library is 10 nanometer.
60 nanometer.
Correct. So it would be 60 nanometer. If I violate, DRC will come. Okay, so again this is active area for the NMOS. So you see, this is how is done. Now why I want to, if I have left this space, we might think that it could be a waste of this chip area, right? Because here in this I can draw another layer of a transistor, maybe a routing purpose or something. If I have another transistor here, I can make the connection with that, right? So yes, so there is a possibility. So you see, I have drawn a metal layer here for some purpose maybe, and then also I have set, I had to follow some rules. So it says that from this active area, the metal layer, extra metal I have drawn, I call it a metal track. That should have minimum 4 lambda. The width of metal itself is 4 lambda, and from each of the active areas I am having a distance of 4 lambda. So these rules, there are a lot of rules, but they are all very simple and straightforward that layout engineer will follow. And again, layout engineer means if you have a 1000 transistors to make a particular logic, so you are not going to place all individual transistors in the software and draw the manual routing using the metals between them. Auto routing will come. Have you done the PCB yourself ever? PCB design? So auto routing in the EDA tool will allow you to automatically connect these transistors together. So first, only task of a layout engineer would be to place each of these transistors at a proper place so that the interconnection between them will be optimized and compact, and the final layout will be compact. Otherwise you might come across an issues of speed, because it's a digital design, power and area, and of course then all this leads to performance. Okay, so example, a stick diagram is given. A stick diagram is to be drawn for a CMOS gate that will compute this function. What is this function? We are very familiar with this now, right?
Yes, sir.
So can you relate with this logic equation to this circuit?
Yes, sir.
Good. So how would you start? And can you just take 5 minutes and draw it on your copy next to you quickly? You know how now stick diagram looks like, layers. You can use color for each of your layers, it's up to you. You can use solid lines or dotted lines, whatever, it's up to you. That's up to your creativity. I give you 2 minutes or maybe 3-4 minutes, draw it quickly, and we will check then. Are you going to draw? All of you are drawing or not? Hello?
Yes, sir, we are trying.
Good. Okay, just we'll wait for 2, 3, 4, 5 minutes and take your time, and we'll move ahead then after knowing your answer. When done, just say done so that I can move to next slide.
Sir, for us it will take time, sir. Okay, you can take
It's
it
okay,
as
no
an
problem.
assignment.
It's okay, no problem. Just let her draw. It's just a matter of 5 minutes or 2 minutes. Okay, so here it will look like this. Just take a moment to understand how it is looking. So again, very simple. You see, I have a 3 transistors here. So how many gates I need? Actually 3 transistors in series, and 3 transistors are in parallel, and the 4th transistor is in series with that. So look at the optimization of the layout. This layout is so compact, and this is how you should learn to draw your layout with paper and pen also, and using EDA tool also. I could have drawn 3 parallel combination just like before, and then somewhere place another transistor to make the series connection of it. But what I did is that the layout is in such a way that this is NMOS, 4 NMOS, and how they are? This is 1, 2, 3 and 4, because poly helps me to understand their division, sources and drain. And then I know that these drains and that's the sources are connected together and they are tied to ground. So you see now, here is the source areas, right? And that's also the sources areas, right? And they are tied to ground. So 3 sources, 1, 2 and 3. And then I know that their drains are connected together. So here is the drain, there is a drain, there is a drain here. So they are connected together right over here. So you just take yourself as an exercise to understand how this routing is done. So very simple. Bottom pull down network and pull up network. Pull up network also says me that this is my PMOS. Okay, and then poly tells me the division, how they are divided. So sources and drain are adjacent to the left and right of each of these polys. And once I know that where are my drains and source, I only want to make 4 connections for VDD, ground, input and the output. So this is how the stick diagram will be used. Okay, so just take this as an assignment again and just try to practice it. So what I would suggest you is that there are notes. I'm not sure if your notes that are given to you, they have such kind of example practice, but in interview they will definitely ask you this kind of questions. So you need to answer those questions, and they will ask you, okay, draw me a stick diagram for this particular logic. So you just say that. There you cannot say, oh, we'll need more time and all that, because this is so simple and so basic, they will expect you to quickly answer. So summary of this would be, we see that at this point what we know. We have seen and we have learned and we now know how mass transistors are acting as a voltage control switches. Why are we calling it as a voltage control switches?
Because voltage is transferring
We are applying
source to drive.
we are applying voltages on the gates of the terminals, okay, and we are performing the switching action. So when there is a voltage, transistor is on. When there is no voltage, transistor is switched off. So that's why we say that we are controlling this operation with the voltage. That's why they are voltage controlled switches. Sometimes we are using this word. What is this?
MOSFET.
MOSFET, metal oxide semiconductor, is very same.
Field
Same.
effect transistor.
Field effect transistor, is it? So are they same?
Yes, sir.
They are same, right? Field effect transistor, again voltage will create electric field, right? So electric field, so we are actually controlling the conduction through the electric field. That's why also they are called as FET. So that's how the FET operates. So we know how they work as a switches, and they are voltage control or electric field control. That's why we also called as FET. We also know that the transistors, how to use and connect those transistors to build the logic gates. So many functions we now know how to create them using the compound logic. Compound logic is, what is compound logic?
The one which you applied. Pull up.
Is the logic of pull down and pull up network, okay? And we also know how we can fabricate those transistors with the bare p substrate. We know all the steps to fabricate these transistors. And finally, we also now know the transistor layout. We know the design rules, we know the lambda rules, we know what is feature size, we know what is resolution, and these are the questions that we'll ask. We know the stick diagram, and using stick diagram we can now create a layout for any logic functions, right? And we also know not only to create that layout but to optimize it, right? So it will need some practice, and that will help you. And we also know how to use the EDA tools. Whenever you will come across the tools, you will know how we can actually optimize the layout using EDA tools and using the function called auto route. So in my opinion, you know enough now to start building your own simple chips. Do you think so?
Yes, sir.
Good. Next topic is design partitioning. What is design partitioning? So when you design a chip, basically, so it's usually a system on chip. You will not be given a task to design a chip about just a D flip-flop or registers or the counters or the arithmetic logic unit. No, they won't. You will be given a big chip design job, of course, and there'll be a team of the engineers usually. So there are like 10 people or 20 people, and there'll be a managers and all that, just like in software industries. So the total system on chip, this particular chip, let's say you are assigned a project to your company to design a microprocessors. Okay, so that is called as architecture of that is called as a system on chip. So microcontroller or microprocessor will have many sub blocks. They are called as okay, so microprocessor in the sense, which kind of microprocessor, what type of microprocessor. So if you remember earlier slides, in one of the slides I have told you that in our laptops, in our computers, we have a microprocessors. Now on my laptop I see on the keyboard it's written Intel inside Core i7. So that's the technology of that microprocessors. In your laptops, if it is a very older version, you might see something written Core Duo or Dual Core. Even before that, you might see Pentium. So these are our architectural names, and they are differentiated by their different functionalities. Each microprocessors have different speeds, power consumption, performance, cost, area, so on. And they have specific instruction sets, they have some limitation, and accordingly their performance is determined. So I have Intel Core i7. It is much advanced than the microprocessor of Pentium. So both are system on chips. So what system on chips in the sense? It will have memories, it will have processors, it will have high speed interfaces, IO interfaces, because this laptop has a computer microprocessor inside, and that has to interact with the outside world also, and outside world data also has to come inside this microprocessor to process. That's how we are all talking to each other. You are sitting in some other city, I am sitting in another city, but we are communicating is because of the high speed interfaces that is helping the computer to talk to and fro from one point, so outside the chip and inside the chip. And we also have a dedicated application specific logic on a single chip. As I said, it means you have analog blocks, you have mixed signal term I have used, right? Mixed signal is analog and digital, and RF, radio frequency, so that's called as mixed signal. So that makes system on chip. Okay, so I just gave you example of microprocessor is a system on chip, and it will have many blocks inside it. So design cost of this system of chips is tens of millions of dollars nowadays. It's so cost, one time design cost, but once it is fabricated, once it is out in the market, then we see that the chips are getting, the cost of the chips are getting smaller and smaller, cheaper and cheaper. Okay, so how to divide this implementation? That's a very big task. Obviously I will not, if I have a team of 10 engineers, I will not ask any one of them to design all the full system on chip. No, I will have to assign memories, processor, interfaces, these analog blocks, digital blocks, RF blocks to each individual engineer, right? So that process is called as design partitioning. So I am just partitioning the specific modules or specific functions or specific architectures among team of different engineers. So that will help to speed up the design cycle and to coordinate. I need to also establish the coordination between the each design team or each individual engineers, just like you might be doing this in your IT industry, the same procedure, but there you design and fabricate software, or I would say you design software. Here we are designing and fabricating hardware. So that's the two different things. So let's have a brief look at this diagram, schematic diagram. What I do, I start with the system specification. So for instance, I'm talking about a microprocessor. So system specification would be how many bits? 32 bit or 64 bit. That would be. Then that's the address bus, data bus, clock. I will have a clock in gigahertz. Some number, specific number can be there, right? So these terms are becoming the specs that come to the company. Whichever company gives this project to a smaller company, or whatever the way it goes, the specs are given to that company or the team. And then we define the architecture. So it's just like a small blank box where inputs are defining and the output is specified, right? So for instance, I said that Y, A or B or dot C and C. So this is like inputs. I know there are 3 inputs that goes to this block A, B and C, and output is Y. So I want to decide what circuit is inside that will create this logic. Okay, then comes the architecture design. Architecture means microprocessor, but then I have to decide what is that microprocessor. It would be Pentium, Core Duo, dual core, or i7, right? They're all microprocessors, but the architecture would be based on their capabilities. So they will say that each will have different clocks, Each will have different instruction sets. Each processor category will have different data bus, address bus. There are different logics, different. For instance, one module in one of the processor, one module I am implementing using multiplexer, and in another microprocessor I am using the same function logic using the latches. In another microprocessor I am using the same function using the transmission gate. So it depends. That is my architecture. So this is the functional design and then logic design, just like what I explained, how many marks, latches, transmission gate, adder, subtractor circuits and all that. Once I get to know that, then I go to next stage, circuit design. This is how the circuit design looks like. I know that logic function right here, and then interconnection of gates will happen. Once the circuit design is done, what we did today, we come to the physical design. Physical design is nothing but I have individual logics. As a physical design process tells me or determines how these logic blocks will be connected to each other with the time clock synchronization amongst them, right? So this part is splitted into these portions. So we have to understand all these things, that partitioning. It means how I will break the complete architecture of the system on chips. Like I said, I have to decide who will design memories, who will design processors, who will design I/O interfaces, who will design analog blocks, RF blocks. So I will distribute this task to my team. Flow planning. Then once all these blocks are getting designed by my team, they will all interact with each other. Then inside this chip, this is SoC, I have to understand and decide where I will put all these blocks, because they have to be connected to each other also, right? They have to understand and communicate with each other. So this is my memory, this is my processors, this is input output buses and all these things. So that's kind of flow planning. And then placement is just like what we see, is that if I have a layout of inverter, if I have a layout of AND gate, layout of mux, so I have to do the routing between them, right? So I have to do their placement near to each other and optimize accordingly. Then obviously when I talk about, I have a latches and master slave flip-flops and all that. So obviously I have a clock, because they are sequential circuits. What's the difference between clock combination and sequential circuit?
Sequential circuits have memory, combination circuits we don't
Right?
have.
Yeah, sequential circuits, output of them depends not only the present state of the input but also the previous state or the past state. Combinational logic or combinational circuits, they only depend on what is available at the input at that particular time. So clock tree synthesis. So this term comes in terms of sequential circuits, flip-flops, latches, and circuits made using flip-flops like registers, counters. We'll see that. Then signal routing. What is signal routing? Once I have NMOS placed, PMOS placed, I have to decide this, draw these metal layers. Poly is already done there, right? All these metal layers, and I have to optimize the layout for the area and the dimension and all that, but tool will take care of it. But as an engineer, I have to understand how I can still optimize. Once the tool will do the auto routing, it is the engineer's job to closely inspect each cell for its placement and then adjust little bit here and there. So once that is done, physical verification, okay, clock tree synthesis, signal routing and timing closure. This is another link to your sequential circuit. We'll see it in detail, how because you have a clock, so you have to understand the timing and all that. So once the physical design is done, physical verification and sign off. So here is the one, because now cells are connected to each other and you have performed all these steps very well. Now you have to understand whether they are performing well or not. I mean, you created this logic function Okay, you got the inputs, you got the output, then you will run the DRC of this block. This is an example, but in actual practice you are running a DRC of system on chip after doing all these procedures. So then you do LVS and LVS. What is LVS? They will ask you this question. Layout versus schematic. Yeah. So DRC is design rule check. Design rule check. LVS is layout versus schematic. And ERC, what is ERC? Electrical rule check. So all these things are there. Electrical rules checks means they will see where is your ohmic drop, short circuits, and all those things. IR analysis, right? And DRC is.
Sir, this DRC, LVS and ERC is done by physical design engineer or someone else?
By the physical design engineer.
Okay, sir.
So DRC design rule check, as I said, and LVS is layout versus schematic. What is your schematic? Like the transistor, whatever, and based on that you have then drawn the layout. So this tool will check. You have 2 transistors in the schematic. Let's say you have 20 transistors in the schematic and you created a layout, and the layout shows like 19 transistors or 21 transistors. By mistake you forgot that. So when you run the LVS, it will show up some error, or it could be another error linked to your layout or schematic. ERC is, they will just see that when you draw the metal routing to connect each of these transistors and make the connections between the circuit, it shows that what is the electrical errors, such as ohmic drops, IR drops, and all these things. Once that is done, if you verify that your physical layout is correct, no DRC. DRC will show that you will see the smile from the tool, because I have done the tape out. So we used to see the smiling face after we clear all the errors, right? And LVS is done usually first, and then DRC is done later. And then you do the sign off. Sign off means you send the chip for the tape out. You have to upload your design file to the library, and that goes for mass fabrication or whatever. Then layout post processing is sometimes you can do some additional steps, but let's not talk about this right now. They're not essential. Some steps are required, we'll see when they come. And then of course this is now not in our control. That chip went to foundry, it's getting fabricated, and then they package it, and it is out on the wafer. You have this system on chips. So they are microprocessor, let's say Core i7 Intel. That is how it is. And then after packaging, the chips look like this, and then it goes to laboratory for the testing. So testing is different. So now my question is to you,